In this video, I want to talk about addition of binary numbers and see how they can be different from addition of decimal numbers. So let's just take a look at a couple of examples. So first, we have an example of addition of two 4-digit decimal numbers. I'm sure you are familiar with this process. So we have 3734 plus 5168. So we start from the rightmost digit. So we have 4 plus 8 equals 12. So we have 2 here. 1 is being carried over to the next digit. Now we have 1 plus 3 plus 6. The answer is 10. So 0. 1 carried over to the next digit. We have 1 plus 7 plus 1, which is 9, and there is no carry to the left. And then finally we have 3 plus 5, which is 8. So the addition of these two numbers equals 8902. So now let's just see what happens when we want to add two 4-bit binary numbers. So for the rightmost bit, basically the least significant bit, we have 1 plus 1. So 1 plus 1 in decimal is going to be 2, right? But if you remember from the previous lecture, 2 is represented by 1 0 in binary numbers. So that means that the result of 1 plus 1 is going to be 0, with 1 carry over to the next bit. Now we have 1 plus 1 plus 1, which equals 3. So if you remember again, 3 in base 10 is equivalent to 1 1 in base 2. So that means that the result of this addition is going to be 1, with 1 carry over to the next bit. Now we have 1 plus 0 plus 0, which is 1 without any carryover. And finally we have 1 plus 0, which is going to be 1. So let's just double check to see if the result of this addition is true if we were doing decimal addition. So this is 1 multiplied by 2 to the power 3 plus 1 multiplied by 2 to the power 2 plus 1 multiplied by 2 to the power 0. This one is 1, sorry. So we have 1 multiplied by 2 to the power 3. This is the one. Then we have 0 multiplied by 2 to the power 2. So I don't add it here. 1 multiplied by 2 to the power 1, which is this term. And then finally 1 multiplied by 2 to the power 0, which if I add all of these together, I get 8 plus 2 plus 1, which is 11. For this one, we have 1 multiplied by 2 to the power 1 plus 1 multiplied by 2 to the power 0. And the result is 3. So now, if we add these two together, the result should be 14. So let's just see if the result is 14. Again, this is 2 to the power 3, 2 to the power 2, 2 to the power 1, and then 2 to the power 0. So we have 1 multiplied by 2 to the power 3 plus 1 multiplied by 2 to the power 2 plus 1 multiplied by 2 to the power 1 plus 0 multiplied by 2 to the power 0. So we have 8 plus 4 plus 2 plus 0, which is 14. And as you can see, these two are exactly equal. So as you can see, the addition is similar to what you have for decimal numbers. The only thing that you need to pay attention to is when you have carry to the next bit. So for decimal numbers, whenever the result of the addition of two digits is greater than 9, you have a carry to the next digit. As for binary numbers, whenever you have the result of addition of two bits to be greater than 1, that's when you have a carry to the next bit. So now let's just take a look at a couple of more examples. So we have here 1001 and 0101, two 4-bit binary numbers that we want to add them together. So let's just go step by step again. We have 1 plus 1, which is 2, and again 2 in base 10 equals 10 in base 2. So we have 0 here, and we have 1 carried to the next bit. Now we have 1 plus 0 plus 0, which is going to be 1, 0 plus 1, which is going to be 1, and finally 1 plus 0, which is going to be 1. So this one, if you convert it to decimal numbers, it's going to be 14. What is the first one? The first one is 9, and this one is 5. Right? So as you can see, the result of the addition is correct. Now let's take a look at another example. We have 1011, and we want to find the addition of this number to 0110. So first we have 1 plus 0, which is 1. Then we have 1 plus 1. The result is going to be 2 in decimal, or 2 or 10 in binary. So we have 0 and 1 carry over. We have 1 plus 0 plus 1, which is again 2 or 10. So we have 0 and 1 carry to the next bit. We have 1 plus 1 plus 0, which is again 0 with 1 carry, and then this one is not added to any other number, so we just write it like this. So as you can see here, we have 8 plus 2 plus 1, which is 11 in base 10. This one is 4 plus 2, which is 6 in base 10. And the result is 16 plus 1, which is 17 in base 10. So as you can see, the result of the addition is correct. However, unlike decimal numbers, which are generally used in basic calculations that we do using pen and paper, in digital numbers we usually have a limit on the number of bits for the binary numbers that we can use. So let's just assume that we are working in a system in which the number of bits for binary numbers is limited to 4 bits. So the first number that we have here is a 4-bit number, and our system can handle that. What about the second one? The second one is also a 4-bit number, but the result of the summation of these two is 5 bits. So that means that if our system is designed to only work with numbers with 4 bits, this number, this 5-bit number, cannot be stored or used in the system. And that is what we call as the overflow. Basically, overflow happens when the result of some procedure in the computer requires more than the specified number of bits that the computer is designed to work with. So again, this is called the overflow. So as I said, again, digital systems are usually operating on a fixed number of bits. So overflow happens when the result of some procedure is too big to fit in the available number of bits. And the example that we saw, 11 plus 6, assuming that we are working with a 4-bit system, results in overflow. Of course, you can clearly see if our system is designed to work with, let's say, 16-bit numbers, then there is no overflow happening when you add these two numbers together, because the result is still less than the maximum number of maximum possible numbers that can be shown using 16 bits. So to say it in another word, if you remember from a previous video, we said that depending on the number of bits that we have for a binary number, there are a range of values that can be represented. So we said that if we are working with an n-bit number, the range of the values that can be shown with n bits is between 0 and 2 to the power n minus 1. So for example, for a system in which n is equal 4, the range is between 0 and 15. The result of this addition is 17, and as you can see, 17 is out of this range. However, if n was 5, in that case the range of the values that could be represented using 5 bits was between 0 and 31. So if we were using 5 bits, then the result of this addition was completely fine, because 17 falls within the range between 0 and 31. So overflow has a direct relationship with the number of bits that is being used to represent binary numbers. So in this video we saw binary addition, and we saw multiple examples of both decimal and binary addition, how we can perform binary addition, and finally we saw how we have overflow as a result of fixed number of bits that a computer system can use.